Welcome back. Today we will be discussing some basic results on topological vector spaces. So let us start with the lemma. Let X be a TVS. Let X be a TVS, and let V be a neighborhood of 0. Neighborhood of 0. Then there exists a symmetric neighborhood. There exists a symmetric neighborhood U of 0 such that U plus U is contained in V. Now I have to tell you what we mean by symmetric. By symmetric we mean that U equal to minus U. That's it. Proof. Given that V is a neighborhood of 0, we know that 0 plus 0 is equal to 0, which implies okay, hence by the continuity of addition, there exist neighborhoods V1 and V2 of 0 such that V1 plus V2 is contained in V. Now take U equal to V1 intersection V2 intersection minus V1 intersection minus V2. Clearly U is a neighborhood of 0, and U is contained in V1, U is contained in V2, right? U is contained in V2. This implies U plus U is contained in V1 plus V2, which is known to be contained in V, right? An easy exercise shows that U is equal to minus U. This is very easy. You can do this at home, right? So moving on, let us come to the first theorem. Let X be a TVS. Let K and C be subsets of X such that K is compact, C is closed, and K intersection C is empty. Okay, then there exists a neighborhood V of 0 such that K plus V intersected with C plus V is empty, right? So this tells us that we can separate, this theorem tells us that we can separate a compact set and a closed set, a disjoint compact set and a compact set and a closed set which are disjoint by disjoint open sets, So these two are this and this. These two are open sets containing K and containing C respectively. So proof let X belong to K. Since K intersected with C is empty, this X doesn't belong to C. This implies X belongs to C complement. Since C is closed, C complement is a neighborhood of X, right? This implies minus X plus C complement is a neighborhood of 0, right? Minus X plus C complement is a neighborhood of 0. Okay. Now, by the previous lemma, there exists a neighborhood U of 0 such that u plus u is contained in minus x plus c complement. Okay. Now again, since u is a neighborhood of 0, there exists a neighborhood Vx, V sub x of 0 such that V sub x plus V sub x is contained in U, right? Now let Z belong to V sub x, then Z plus 0 belongs to V sub x plus V sub x, which is contained in U. So this implies V sub x is a subset of U. Hence we get that V sub x plus V sub x plus V sub x is a subset of U plus U, which is a subset of minus x plus c complement, right? This implies x plus V sub x plus V sub x plus V sub x is a subset of c complement, right? That is x plus V sub x plus V sub x plus V sub x intersected with c is empty, right? This is what it means. Now I claim that x plus V sub x plus V sub x intersected with c plus V sub x is also empty. Now to prove this claim we will use the fact that Vx is symmetric. Right? We will be using this fact. So let us see how we use this fact. So assume Z belongs to this intersection x plus V sub x plus V sub x intersected with c plus V sub x. Okay. Since Z belongs to this intersection, Z belongs to this set, we can write Z as x plus y1 plus y2, and since Z belongs to this set c plus V sub x, Z is equal to some c1 plus y3, where c1 belongs to c and yi belongs to V sub x for I equal to 1, 2 and 3, right? So these two elements are equal, so we get that x plus y1 plus y2 is equals to c1 plus y3. Now I take y3 to the other side. This implies c1 is equals to x plus y1 plus y2 plus minus y3. Since V sub x is symmetric, we get that minus y3 also belongs to V sub x, right? Since Vx is symmetric, minus y3 belongs to V sub x. Now this is a contradiction to this statement, right? If we call this star, so we get a contradiction. This is a contradiction. This tells that c1 belongs to this is a contradiction to this statement. It is a contradiction to this statement. This is what we need to show. This is a contradiction to this statement, because c1 is an element of c and this summation is an element of x plus v sub x, vx plus vx plus vx. So we showed that this intersection is not empty, which contradicts this statement star. This is a contradiction to star, right? Contradiction to star. Okay. Hence we proved the claim. The claim is x plus vx intersected with c plus vx is empty. So we get this. Hence we get this, right? Now this is true for every element in x in K. So let us now we get a cover of K, that is K is contained in union of x plus v sub x, x varying over K, right? This x plus vx is an open cover of K where K is running over K. Now since K is compact, there exists x1 x2 up to xn in K such that K is contained in union of xi plus V sub xi, right? This is because of the compactness of K, right? Now there is a natural choice of V now, so let us take V equal to intersection of V sub xi, I varying from 1 to n, right? So this is the natural choice of our open set. So V is a neighborhood of 0, V is a neighborhood of 0. So let us look at K plus V. So K plus V is contained in, K is contained in this union. So this K plus V is contained in xi plus Vxi, right? Xi plus Vxi plus V, which is actually equal to, it's a easy exercise to show that this is equal to xi plus Vxi plus V, which is a subset of union of I varying from 1 to n xi plus Vxi plus Vxi, right? This is because V is a intersection of all such Vxis. So I am adding a bigger set, so we get this inclusion. This inclusion is clear, right? It's because V is a subset of V is an intersection of each of these Vxis. Now let us look at C plus V. C plus V is contained in C plus Vxi for all I varying from 1 to n, right? And C plus Vxi intersection with xi plus Vxi plus Vxi is empty, right? It's empty. Why is it empty? It's empty because we showed it is empty. It's true for each x in K, and xi's are elements of K. So C plus Vxi intersected with xi plus Vxi is empty. So we observe that C intersected with each element of this is empty, right? So C plus V intersected with this union is empty, right? Hence this K plus V is a subset of this union. So we can conclude that K plus V intersected with C plus V is empty. Is that okay? This also tells us that K plus V is contained in C plus V complement, right? This is something which you need to note. This completes the proof of the theorem. So we are making a side note. So K plus V is contained in C plus V complement. Now C plus V is an open set, so C plus V complement is closed, right? And K plus V closure is the smallest closed set containing K plus V. Hence K plus V closure is contained in C plus V complement, right? This implies K plus V closure intersected with C plus V is also empty. In particular, K plus V intersected with C is empty because C is a subset of C plus V. So we'll keep a note of this. So moving on, we have two corollaries of the previous theorem. Corollary: let X be a TVS. Let B be a base of X, local base of X. B be a local base of X. Then every member of B contains the closure of some member of B. Okay. Proof: let V belong to B. V is some neighborhood of 0. V is a neighborhood of 0. This implies 0 doesn't belong to V complement, right? And V complement is closed. By previous lemma, singleton 0, which is compact, singleton 0 intersected with V complement is empty, right? So by this note and by previous theorem, there exists a neighborhood W of 0 such that singleton 0 plus W closure intersected with V complement is empty, right? But singleton 0 plus W is nothing but W, right? Because we are adding nothing to W. So we get that W closure is contained in V complement. W closure intersected with V complement is empty. W closure intersected with V complement is empty. Now since B is a base, B is a local base, there exists a neighborhood. Okay, there exists U belonging to B such that U is contained in W. This is by the definition of local base. This implies U closure is contained in W closure. Hence, U closure intersected with V complement is empty. This implies U closure is contained in V, right? This is what we needed to prove. So this proves the corollary. Moving to the next corollary, it's a simple corollary. Every TVS is a Hausdorff space. Proof is very simple. Let x comma y belong to x, where x is not equal to y. Then singleton x is compact and singleton y is closed. Such that singleton x intersected singleton y is empty. It's empty because x is not equal to y, right? So there exists V, a neighborhood of 0 such that singleton x plus V intersected with singleton y plus V is empty, right? So this is a neighborhood of x, this is a neighborhood of y, and we showed that we get a separation of singleton x and singleton y. So we can separate distinct points by disjoint open sets. So this shows that every TVS is a Hausdorff space. Thank you. We'll meet in the next class. Thank you.